chapter 3.2 continued, talking about what an outlier is. So an outlier is an observation or observed value or point that is outside of the x or y values of the overall data. And an observation is influential if, by looking at it with the value or without the value, does it change the slope or y-intercept substantially? Okay, by being included or not being included. Or not included. So, and that's an important fact with working with outliers, is you need to run the linear regression with the outlier, and you need to run the linear regression without the outlier to see if that outlier is influential and to help you make a decision. And outliers in the x direction, they tend to be influential. Okay, so those x direction outliers, pretty dangerous. And outliers in the y direction tend to not be influential. So if you do suspect an outlier, then you will have to perform your linear regression with the outlier. Then you will have to run it again without the outlier. Then you will compare the results. If you found that there is a big change between these two things, then you should lean towards using the data with the outlier, unless you have a very clear reason why you feel like you can remove that outlier. But if you see that there's a difference between the results, generally we go with the outlier, but you would mention that it could be very important in changing the results of your final answer. Okay, so here's an example from the textbook, the Gesell scores, and these are basically like an intelligence score. And what they have done here is they have these children where they measured at what age they said their first word in months, and then they're basically this Gesell score, which is supposed to be like an intelligence score, aptitude, I guess is probably a better word for it, aptitude score for the child. And so then you can see they've plotted the data. Now, who's an outlier on here? As you look at this general trend of the data, this child 19 is higher than any other y value. That gives the potential for this child 19 to be an outlier in the y direction. Similarly, this child 18 also is a lot lower than any of the other values, and so this child 18 could also be considered a outlier in the y direction. But how influential, we'll continue to look. Now on the x direction, as I look here, this being the last window of the x values, that's telling me this child 18 is very extreme compared to the other X outlier children. Now, if I add another child, I'm going to add a child right here, this green dot I'm adding, pretend there's a child there. That child would not be considered a Y outlier because notice that child is within the Y values, but that child would be considered an X outlier because that child is well outside of the green window of X values of that for the regular data. So I'm going to remove that person though because it doesn't really exist. All right, so that's basically how you use your judgment on if they're an outlier. And so then they made a residual plot. Recall what a residual plot was. It's taking your observed Y value and subtracting that predicted Y value. That was gotten from, calculated from your model. And so this is then plotted versus X. So like these are the X values and these are the residuals, which is, you know, this how far off it is. And so when I look at those, yeah, like child 19 has a really large residual. That's kind of problematic. Child 18 does not have a very large residual. But as we learned from the other page, X outliers tend to be really influential, and let's see what happens. So like someone would need to run this model with all the children. And so that's what they did. They ran this model with all the children. They got a correlation coefficient of 0.64. So I guess I would call that a moderate negative model. I have to look at the graph to see if it looks linear, somewhat linear. So negative. And this was the predicted Y is 109.874 minus 1.127x. That's with all the children. If I remove my child 19, who I think is a Y outlier, you can observe that that Y outlier does not change the model very much. So a not very influential outlier. And so if there was no child 18 and this was the results I got and there was no child 18, I would go with the model using all the children. But now let's put in child 18. We'll look at child 18, and that is an X outlier, and let's look at what happens with child 18. So when we look at child 18, we see that our correlation coefficient drops substantially to negative 0.33. This, to me, tells me that my model is probably actually not a very good model, and really the influence of child 18 was taking over the entire model and forcing the model, the graph of the line, to just go towards that child 18 point and really not. So let me just see what this. Just going to see what this. Whoops, 0.33 squared. Okay, so like, see, only, you know, not even 11% really. See, 10.9% of the variation in the Gesell adaptive score can be accounted for by the model of Gesell adaptive score on age of first word. That 10% does not seem like a very good model. So you can see that with child 18 removed, we see a substantial change in the model. I actually think that this is probably a more appropriate model than using all the children, but it also clearly shows that it is not a very good model at all. And so probably whether you had an outlier or no outlier, this is not a good model to determine somebody's intelligence just based on how old they were when they said their first word. So those are outliers. So then just to talk about data output, and you're going to have examples of this in the book. So have to be able to read these because there's clearly a lot of work to doing a linear regression if you're doing the entire thing by hand. So it's really, really common for the AP test to give you some of the graphs already made and even to give you data output where they've already run a regression. And so here is a regression. So first of all, correlation is the number which describes your direction and strength of a linear relationship. The form that we need if we are doing linear regression must be linear, but we can only see that with a graph. In order to do linear regression, we must have bivariate data that is quantitative. Both the values need to be, variables need to be quantitative. Least squared regression requires an explanatory and a response. It is not always clear which is which. And for linear regression to be met, it must meet the nearly straight. If your graph does not look nearly straight, then do not perform a linear regression, either like this or like this. If it's not looking straight, linear regression is not appropriate. So here's some sample output for blood alcohol content versus beers. And they have the regression equation, which has been written. And the only, if you were writing this, of course, you would put a hat on it. They can't do that with their output. And they've written the equation. How'd they get it? So the constant will describe your y-intercept. And the beers will describe your slope, with the first number under coefficient here being the y-intercept and the slope. So let's label what these important items are, just that you can keep track of it. So b sub 0, which in physics they'll say b naught or b sub 0. That is your y-intercept. Then b sub 1 is your slope. And you can see the b sub 1 and the b sub 0. Okay, the letter S right here. This is our standard error of the residuals. That measures how far off on average you tend to be, and the units will be the same as y. Okay, then we have our r squared. That's our coefficient of determination. And let's go through and just see if we can identify all these things on here. So here was our y-intercept. So that was negative 0.01270. Our slope being right below it, that's equal to 0.017964. Our standard error was 0.0204410 BAC units, whatever they are. You might think that might be percent. Coefficient of determination, right here. You'll never use this. So 80.0%. And could you find R from this? Yes. So to do that, R will be the square root of R squared, but you cannot use the percent version. So let's, as a decimal, so square root of 0.800. And since I am taking the square root, it could be the positive or the negative. So I get 0.8944, but which one is it? Because slope is positive, because remember the R value describes the strength and the direction. Since the slope is positive, then R is positive. And so we're going to use the positive. So R is positive 0.8944, which I would say is a strong relationship. And if you look through that same paper, like what other errors did they have on there? What I mean by that was the SE coefficient. Whoops, it just has one F. If you look at the SECOEF column, if you look on that, there was the standard error for the constant. That's roughly how much. This is the average variation in Y. Intercept. You'd expect on average when you, whoops, intercept, when you do this model many times, intercept, you expect that Y to vary by that. And then there's a standard error of the Beers, which is the standard error of the slope. Which on this thing was 0.002402, and that would be BAC per beer. And that is on average, you expect the slope to vary by that much every time you average variation in slope. So if you did this model over and over again, went out, gathered new data, you'd expect the slope to vary by about that much. And then, of course, you saw the SE, the letter S, which was our standard error of our residuals. Which we've already talked about right here. And based on that, do we think this is a good model? Let's look at this standard error of our residuals. Let's look at our R squared and use some judgment. Do we feel like the number of beers is a good predictor for what a person's blood alcohol content will be? And so the average prediction error for our model of blood alcohol content on number of beers is approximately 0.0, gosh, what was it? 2044 BAC units. Okay, so we seem to be off by about, I think blood alcohol content is percent, so it's like 0.08 is over 0.08, then you're considered impaired. On average, our model predicts blood alcohol content is 0.0204 off compared to the observed BAC values. That's just another way of saying the same thing. I mean, that's basically our prediction error. Considering 0.08 is the legal limit, it might be understandable if someone was at 0.1 or 0.06. It'd be kind of understandable if they had that and they drank the same amount of beer as someone who is 0.08. Coefficient of determination, the R squared, written like that or like this. You'll see both of those either way. That's the fraction of the variation in the values of y that is accounted for the least squared regression line of y on x. So just to be able to write that sentence, since R squared was 0.800, approximately 80% of the variation in BAC is accounted for by the least squared regression line of BAC on the number of beers consumed. So at 80%, I would say that it does seem to be a somewhat good model to predict your blood alcohol content, but clearly not perfect. So based on the S equal 0.0204 BAC and R squared equals 80, this model does appear to help predict, to give, I would say, maybe a rough prediction estimate of BAC using number of beers and appears helpful. Yeah, I'd say that's a helpful model. And I'm going to stop the video and do a second video for this page, which will give you the example and help you with the mini quiz.